Alright guys, we're going to be talking about mass-to-mass conversions today, and if you've had chemistry before, you may have heard that that's called stoichiometry. You can actually predict how various reactions will happen before you even do them. So you can actually get desired outcomes by just kind of controlling some of the reaction conditions. In this reaction, I've got sulfur reacting with nitric acid, and we're producing sulfuric acid, a nitrogen dioxide gas, and water. I'm going to go through this and balance this really quickly, and that's the very first step. Before we can actually do any kind of mass-to-mass conversion, we first have to have a balanced chemical reaction, and now that we have one, we can actually kind of get into how would you actually solve a mass-to-mass kind of conversion. So the idea here is maybe you, for whatever reason, you have a specific situation where you would like a specific amount of one of these chemicals. Maybe we want to produce sulfuric acid, and we want to make 500 grams for whatever purpose. It might be for a fertilizer, maybe we need the acid itself, but we want to produce 500 grams of this. So this will be our first example. Alright, here's our first example. For whatever reason, Mr. Parson needs 500 grams of sulfuric acid, H2SO4. What mass in grams of HNO3 would be needed to produce the desired product? So really what we're looking for is, before we do this reaction, the ask is, how much nitric acid do I need to start with in this reaction with sulfur to produce the amount of H2SO4 that I want? So now there's a few things that we'll need to address this. One of them is going to be the molar mass of each of these. So first, if we remember, 1 mole of anything, in this case, H2SO4, 1 mole of HNO3, we need to know how many grams each of these weigh. So I'm going to really quickly do the molar mass for each of these. For H2SO4, our molar mass is going to be 98.072 grams. And for HNO3 looks like it has a molar mass of 63.012 grams. So we have molar masses of each of these. Those will be important because one of the things that Mr. Jordan just recently taught you was there is something called a mole-to-mole ratio. That is another piece of information that we need to kind of collect and recognize here. What I'm seeing from our mole-to-mole ratio, remember those come from our balanced chemical equation here. I see that there are 6 either moles or molecules for every 1 of the sulfuric acid. So we also have this ratio. We have this equality too. 6 moles HNO3 will be equal to 1 mole of H2SO4. So here's the idea of how to actually go about solving a mass-to-mass conversion. We have a desired amount in grams of H2SO4. So just like any of our other problems involving these t-tables and conversions, the 500 grams will be our starting value. That's how we'll kind of start off the t-table. And our goal is to get from grams of this chemical to the grams of this chemical. This is all the information that I think we should need. I don't think we need anything beyond that. The idea here is, while this is in grams, we can use its molar mass to get into the world of moles. In the world of moles, we can actually change which chemical we're talking about by using this balanced equation. And that comes from our mole-to-mole ratio here. Once we're in the land of moles of H2SO4, you can see that that kind of aligns here. I can actually move into a different chemical now. I can actually switch to the moles of HNO3. Once we're in the moles of HNO3, notice that matches here. We can use this molar mass to get us into the grams of our final desired answer, which is grams of HNO3. Grams HNO3. I'm going to go ahead and start setting up our t-table. And to start, we're going to place 500 grams. Remember to place nothing underneath. And then right away, I can start to put the grams of H2SO4 here. And the reason I'm doing that pretty much automatically, we know that in order to get rid of this unit I don't want, because I need to get to grams of HNO3, I need this unit to cancel, and the only way to get it to cancel is by having it diagonally down. and we're going to have to divide by that. On top here, the direction I want to go is moles. In the world of moles, we're able to kind of convert between things. That's kind of the fair place that allows us to do that. So moles H2SO4 go up on top. And I'm going to continue with this t-table, but not actually putting in the numbers yet. This is not my answer. I need to keep going. I'm not actually at grams of HNO3 yet. So I know that this unit also needs to be canceled. Move it diagonally. And it's at this point that I want to switch from moles of H2SO4, the sulfuric acid, to moles of our other chemical, the nitric acid, HNO3. If you guys remember, anytime we see moles and grams in the same area of a t-table, that's going to be molar mass. Anytime you have a part of your t-table that is moles of one chemical and moles of another chemical, that's the mole-to-mole ratio that Mr. Jordan was talking about last week. Now our last step, because we're still not there, we're not at grams of HNO3, I need to once again cancel this unit, and my final unit is in fact those grams. Now I can actually start to fill in the values that go along with this t-table. Remember, molar mass, and that's going to match these values here. So for 1 mole of H2SO4, moles of H2SO4, I'm going to have this many grams for my molar mass. So I'll place 1 next to mole, 98.072 grams H2SO4. The next place I'm going to go is my mole-to-mole ratio. This part of the t-table, moles of one thing, moles of another, that's going to be this mole-to-mole ratio. Remember that these numbers come from the balanced chemical reaction above. So just know that that's where those are coming from. I will put 6 next to moles of HNO3, 1 next to H2SO4. Finally, at the very end here, we're going to be filling this in with our molar mass of HNO3. 1 will go next to mole, and 63.012 will go to our grams of HNO3. Now I just kind of double check here, make sure that I'm doing my t-table correct. I can go through and cross out any units. So grams of H2SO4 are going to cancel grams of H2SO4. Moles of H2SO4 cancel our moles of H2SO4. Moles of HNO3, moles of HNO3. And then I get to the grams of HNO3, which should be the answer that I'm looking for. The idea here, remember, is we can produce 500 grams of H2SO4 if we actually start our reaction with the right amount of our reactant. So I'll go ahead and put this into my calculator. Remember, we multiply everything straight across, so all of these get multiplied. And then anything down below, I'm going to be doing division. After I put all of this into my calculator, I got this as an answer. And before we record that as like our final value, remember that we need to keep track of sig figs. In our original number, I am seeing 4 significant figures. That means in my answer, I should be matching that same level of significance. And because we have a 5 afterwards, I'm going to have to round this. So my final answer would be 1,928 grams of HNO3. Now I know that this just looks like a whole bunch of t-table stuff, but if we actually look at what this is saying, this is pretty powerful, because what we're looking at is we've done none of the chemistry. We've actually pulled out none of these chemicals, and we haven't actually tried this. We are predicting that in order to produce 500 grams of this product, we would need to start with 1,928 grams of HNO3. And that's why we call this a mass-to-mass conversion. Where you are starting is a place in grams, and where you're ending is also in a place of grams. Let's do a second example so we can continue to see how to set this up. Maybe instead we have a very different situation here, and for the second example, maybe what I'm looking to do here is I have some constraints. Maybe this time around, rather than looking for a product, I have some constraints on just what I have on hand. Maybe, for whatever reason, sulfur, I have a very limited quantity of this. I happen to put all of the sulfur that I have on hand onto the balance, and its mass is 76.8 grams. And maybe this time I don't care about the sulfuric acid. Maybe I'm actually looking to produce the nitrogen dioxide on the other side. So this will be our next example, example number 2. So here's example 2. Mr. Parson only has 76.8 grams of sulfur. how many grams of NO2 could be produced if all of that sulfur were to react. So very similar to before, this is mass-to-mass conversion. I'm going to need a few pieces of info. So let me kind of collect that info. I should probably have the molar mass of all of these on hand. So 1 mole of sulfur. If I look at the periodic table, I don't have to actually do any calculations here. I can just copy this. And then for 1 mole of NO2, in this case I'll have to do a little bit of math. So I'll go to my calculator here, and it looks like the molar mass of nitrogen dioxide is 46.005. Finally, the last piece of information I'll need is our mole-to-mole ratio. The ability to go in between moles of one chemical and the other is kind of the essential part here of this mass-to-mass conversion. So if I look back up to my balance equation at the very top here, I'm specifically looking at sulfur, and it looks like we have 1 mole of sulfur, or 1 molecule of sulfur, and its relationship to the NO2 gas is 6 moles. So I'll record all of that information too. Just like in example 1, we'll draw a relatively long t-table because this has got several steps. My starting value, 76.8 grams of sulfur. Nothing will go underneath there. And just like in the first example, I'm going to anticipate that I need to make this unit get canceled, so I'm going to copy it down below here. And the place I want to go in this first part of our t-table here is I'm going to use the molar mass so that I can enter the world of moles. Again, I'll copy those units, the moles of sulfur, because that is still not the unit that I actually want. I want grams of NO2, so I'll keep on going. In this next part of our t-table, remember that this was the molar mass of sulfur. And if we look above to kind of see where we went next, the next spot is a mole-to-mole ratio. We have 2 different types of moles stacked on top of each other. So this is the area where I can shift from moles of sulfur to moles of NO2. Finally, I can go to my grams. Now I can go ahead and fill everything in. I've got molar mass of sulfur here. Moles and grams in the same part of the t-table means molar mass. So I'm going to pull this information in. I'll put 1 next to moles, 32.06 grams of sulfur. In the next area, we're going to have moles to moles, mole ratio. So that's where I'm going to pull in these numbers. Remember that the 1 here and the 6 here came from the balanced reaction above. So we'll place 1 next to moles of sulfur, 6 next to moles of NO2. And then in the very last part of our t-table, we're going to be going with the molar mass of our nitrogen dioxide. So that is 46.005 grams and 1 next to our moles of NO2. I'll go ahead and just double check that my units are canceling correctly. I've got grams of sulfur being divided by grams of sulfur, so those units cancel. Moles of sulfur, and moles of sulfur. Moles of NO2, everything's canceling, and I do get the desired unit of grams of NO2, which was what I wanted from my original example question. Now I can put this all into the calculator. I'm going to look ahead though and just verify the number of sig figs in my original number here. Looks like we have 3 significant figures. So when I do this calculation, my answer should also have 3 sig figs. I just entered this all into the calculator, and accounting for the 3 sig figs, the answer I get is 661 grams of NO2. Alright, that's how you do your mass-to-mass conversions. Go ahead and call us over if you guys have any questions.